Hello, and thank you for joining today's Family Office Network's webinar series featuring EPS Holdings. Before we get started, I would like to take a minute to introduce our speakers today. Michael Daly, President and CEO of EPS. Mike has been involved with the company for the past 10 years. Over that time, Mike has been focused on raising capital for EPS and working with Brayton Energy on the design and development of the turbine engines. Mike is a professional accountant by trade and served as CEO and CFO of several financial institutions. Also with us today is Jim Kesseli. Jim has worked in the energy conversion field for 40 years. Jim is founder of Brayton Energy, managing its 50-person technical staff in the development of turbo machinery for advanced energy conversion. Jim's career started at Lockheed, working on gas turbine projects. Jim also graduated from MIT with an MS in aero engineering. At the end of today's presentation, we will have time for Q&A. Please use your questions chat option on your screen to send any questions you have so Mike and Jim can answer them accordingly.
Thanks, Lindsay. Good afternoon, everyone. As Lindsay mentioned and introduced me, my name is Michael Daly, and I'm President and CEO of EPS Holdings. As Lindsay mentioned, in addition, we have Jim Kesseli with me here today. Jim is President of Brayton Energy. Jim and his team at Brayton have been huge supporters of EPS. Brayton is a design and engineering team located in Hampton, New Hampshire, and have been instrumental in the design of our turbines. And I'm pleased to have Jim join me here today. Jim will explain more of the technical aspects of our unique turbine technology throughout the presentation today. First of all, I'd like to thank all you participants for sharing your time with us to learn more about this exciting new venture that we believe will make a significant inroads in the distributed energy and renewable energy space. In our presentation, we are going through the PowerPoint presentations you have access to and hopefully is up on your screens now. We have a lot of time for questions and answers at the end of the session, but if you have additional questions, Jim or I would be keen to speak with you one-on-one over the next few days. Before we begin, I'd like to thank Lindsay Shuck and Audra Plageman and their team at Family Office Networks for assisting us with this presentation and providing an opportunity to speak with you all today. Firstly, we have a very powerful corporate objective to become the preeminent leader in the distributed energy generation through advanced turbine engine technology development in the next 7 years. I'd now like to go through how EPS intends to accomplish that objective. I think the critical question is why EPS exists and how do we get to where we are today. Although I will not be reading directly from the slide deck today, I think it is important for me to highlight each of the bullet points on this particular slide. EPS believes that the distributed energy sector, sometimes also known as DE, will be one of the fastest growing energy markets for many years to come. Distributed energy is where the end power users effectively go off the grid to produce their own electricity independent of large central power stations. DE is currently dominated by noisy, bulky, high emission producing and costly to operate reciprocating engines, sometimes called diesel engines or recips as they are referred to. And those recips are EPS's major competition. EPS believes we have a very viable solution to service the DE market through the production of our small scale turbines that are cost competitive, very efficient, and easily transportable while incurring a lower operating and maintenance costs and producing very few emissions compared to its competitors. EPS believe that the small scale, which is the 1 to 5 sector, engine size sector, have been significantly underserviced by large-scale turbine manufacturers such as Siemens and GE, who are only focused on manufacturing larger frame engines. Generally, larger scale turbines in excess of 50 megawatts are highly efficient, while smaller scale turbines are significantly less efficient. The game-changing premise, or EPS's secret sauce, is that we have found enabling technology to capture the high efficiencies found in large-scale turbines and incorporated that technology into our small-scale turbines through a patented process. So to be clear, we're not wind power or solar power. Our sole focus is manufacturing small-scale turbines to produce primary power, not backup power, using a variety of fuel sources in the distributed energy sector. First, a summary of what our plans are and where we are today. Our goal is for our turbine engines, the EPS engines, to have the best-in-class efficiency, have the lowest O&M costs, lowest emissions, longest operating life, and have best system uptime availability. We're going to focus on manufacturing through assembly only our turbines in the 1 to 5 megawatt power range. That is considered small scale. Some would even classify these engines as micro turbines. Initially, we will produce 2 turbine engines. One will be a 1.6 megawatt turbine that will use any form of liquid or gaseous fuel and as its fuel sources, and the other will be a 1.2 megawatt biomass turbine that will run on any form of solid waste biomass. The key is that our engines will compete very favorably against the diesel engines that currently dominate this engine size space. EPS turbines will provide primary power for many end user groups using an abundance of fuel sources. We have about 8 years in development under our belt already. We've raised and fully deployed $4.5 million US in cash common share equity received from about 35 shareholders and raised an additional $1.5 million through preferred shares in this initial development stage. The patented enabling technology, the intellectual property, has been arranged through a draft 20-year royalty-free license arrangement with our design and engineering partner, Brayton Energy, but more on them later. We have built and successfully tested a quarter-scale model of the biomass combustion chamber. We have 2 customers that have signed letters of intent to purchase significant quantities of our turbines. We anticipate that we'll be ready for full-scale commercial production in approximately 2.5 years after the alpha and beta stage testing is complete. What EPS is looking for right now is up to $18 million in US dollars from one or multiple investors to be received over the next 10 quarters to complete the development stage and move forward towards full-scale commercialization, but more on that later as well. Although I will go into some financial highlight detail later on in the presentation, our first production engine is scheduled to be built in Q2 of 2023. We anticipate receiving progress payments or cash advance payments on those first commercial orders, and the first such payment is expected to be received in Q1 2023. Our indications for initial sale prices for engines are about $1.44 million for our 1.6 megawatt multi-fuel turbine, and the sale price for the 1.2 megawatt biomass turbine is about $1.8 million. Our financial model is indicating that our gross profit margins will be running about 37% at full production volumes, with ROEs exceeding 90% by year 5. The key point here is we have customers waiting to purchase significant quantities of our turbines. I'll now turn it over to Jim to give some more technical aspects of our turbines. Jim?
Thank you, Mike. So yes, well, the picture on slide 8 shows a layout of the package. Some more dimensional stuff coming later, but on the right-hand side, the box that says EPS, that's the recuperator and combustor assembly. The middle element there, which is the turbo machinery, and on the left-hand side is the power electronics for the particular application. Next slide, please. So yeah, the key takeaway for the engine is that it is a somewhat different architecture, and it incorporates what we refer to as a recuperated intercooled gas turbine engine. So it's the benefits of the intercooler and the recuperator propel its efficiency to a substantially higher level than current gas turbine engines, which I'll talk about later. But roughly, we're targeting efficiencies over 40%, and the competitive gas turbine engines are in the low 20s, so almost 2x twice the efficiency of the conventional gas turbine engines. And with that, we've adapted some modern technology for emission control system, integral emission control system without any after treatment requirements. So it's a very clean burning system. And as will be stated a few times, it's designed to use a number of emerging fuel types coming along. Next slide, please. So, okay, this is a bit of more of a cross section. Bigger picture will be better, but on the right-hand side again is this is the biomass burning version of it. So the work that is done is two variants of the engine that are going to be described, or sort of physical embodiments of the engine. One for conventional liquid fuels and natural gas, and the other one burning solid fuels. Mike, why don't you put your mute on? There's a lot of side notes or background noise. So that's better. So on the right-hand side is the combustor for burning solid fuels, and the work in this area came from extensive research on bio-derived fuels like digester gas and bio-oils. While we could burn those, they are and very good efficiency. Those fuels have been so expensive, it's just not been economical to generate electricity with those expensive fuels. So the work that our novel activity has been involved in burning directly the solid fuels. That is the very novel aspect of it. And that the rear chamber at the back on the right-hand side of this picture is the zone where we would burn sawdust or any kind of pulverized material. So next slide, please. So I think I'm going to summarize a few things here. So again, our work has been on testing, and I'll show some test rig that we use to develop the combustor for directly burning solid fuels in the gas turbine environments. We preserve the characteristics of the gas turbine, its multi-fuel capability, its very long life potential, and it's in very low emissions. And we're adapting it to burn solid fuels from agricultural waste or cellulosic material, emerging work on algae and other bio-derived fuels, and of course wood chips and pellets. So that's the key novel aspect of the engine. Again, there's a conventional version of the engine for natural gas and other conventional liquid fuels, and then there's the solid fuel burning version of it, which I just showed in the previous picture. Next slide, please. So this is sort of a schematic arrangement of how the engine is configured, and it shows some of the novel characteristics of it. There's starting from the left-hand side, there's an alternator connected directly to the shaft, so it's a single shaft gas turbine engine. And the flow in between the two centrifugal compressors, the CL and CH, those are the two centrifugal compressors. In between that is an intercooler, very conventional heat rejection system that can be used for space heating or some other cogeneration applications. And then also on the same shaft are two turbines. There's two axial turbines on the same shaft with two centrifugal compressors, and that's all has an output load on the cold end drive or the alternator. The recuperator in the combustor or the burner are integrated together into a single module that I showed in that layout earlier. And basically, so it's a novel feature is that it burns the solid fuel at atmospheric pressure. So there's no need to deliver the fuel pressure or fuel supply over the pressurized boundary. Rather, it's essentially inhaled into the engine at the exhaust where the static pressure is quite low, and we use a blowing or conveyor system to blow the sawdust in there and burn it. The recuperator delivers the heat across the pressure boundary to the turbine. Next slide, please. So this is our combustor test rig. I'll just go through it quickly here. Essentially, again, there's no gas turbine engine in this picture here. This was just a system to develop the combustor in parallel with the work that we're doing on the turbine machinery development. So it used essentially a blower with a preheater simulated the turbine exhaust, and that is the principle that we're using. We're burning essentially the solid fuel, the biomass, the algae in the very high temperature turbine exhaust and raising that temperature up to the turbine inlet temperature. So on the left-hand side is just basically we used a common spreader system as a sort of a salt spreader from a municipal activity. Basically just something to dump the solid fuel into the duct, which was then conveyed or blown into the turbine exhaust simulation. Next slide, please. So again, another rendering of the picture, a list of some of the fuels that we've tested, and again, we are definitely obviously concentrating on renewable fuels. This really separates us from the competitor engines. They're not only very inefficient, they have no way of burning some of these unusual fuels. And the piston world of engines, which I'll talk about later, also has no really practical way to burn many of these. They're either diesel engine or gas or natural gas engines are very well developed and very competitive, but they cannot use this range of renewable energy fuels as we can with this purpose-built EPS engine. Next slide, please. So in summarizing, it's very high efficiency, again, roughly twice the efficiency of our competitor gas turbine engines. There is the potential for using the waste heat from the turbine machinery to provide additional energy recovery for so-called cogeneration, domestic water heating, drying, municipal or drying applications or such things. And they have been, this is a more common area for distributed generation. This is cogeneration for universities and larger hotels and thermal and hospitals. But principally the attribute is in burning renewable fuels and doing that very efficiently. Item 2 is the low maintenance cost. The engine is really only one moving part. It has the rotating assembly that carries the 2 compressors in the turbine, and the alternator is on that same assembly. And that results in a very simple long life system. It's very conservatively designed, modern aerodynamics, but also very conventional in its boring system. And again, that shaft speed alternator enables variable speed and some other great features which improve efficiency and reliability. And then the last point is the exhaust emissions. There's, of course, a lot of pressure in the EPA and around the world, and particularly in most stringent areas of California, to control nitrous oxides or NOx, so-called NOx, and CO and unburned hydrocarbons. And while piston engines, spark ignition gas engines require, and diesel engines require catalytic after treatment systems, this engine does not require any after treatment. It's just a very clean burning system, and an attribute of many gas turbine engines, but we've gone the extra distance to make this an extremely low emission engine using modern combustion techniques. Okay, next slide, please. Okay, so I think in summary also, I should say that every component in the system is designed for a 60,000 hour life. And that is not that unusual for gas turbine engines. They're commonly designed for very long extended operation. This engine operates at relatively moderate temperatures and speeds and stress levels. It's very conservatively designed for the application, and again uses conventional bearings and systems that have been well proven in the field. The goal for the low O&M cost is to have only service intervals every year, 8,000 hour service intervals, where things like filters and other checks, lubricants and other sensors are checked out. But again, we're not anticipating any significant maintenance over the 60,000 hour life period. Next page.
Jim, I can.
Okay, so back to you, Mike.
Okay, thanks. Thanks, Jim. So in summary, there's been considerable interest when evaluating the benefits of the EPS turbine versus another small scale turbine produced by a competitor or a reciprocating engine. To summarize, and Jim has gone over some of these points, EPS turbines are available in either a liquid or gaseous fuel version or the solid waste biomass version. There's a strong commonality of parts. There's, in this engine size, there's no other biomass turbine that exists. Our engines produce very low emissions that will meet or exceed the North American and EU emission standards. They're also scalable up to 5 megawatts. What we've been talking about here and what Jim has showed you is our initial units, the 1.6 megawatt multi-fuel unit and the 1.2 megawatt biomass unit, but they are scalable up to 5 megawatts. We've had a lot of attention or interest in the 3 megawatt version size. They can be formed if we put in series to form a power substation. And the key here, they're lightweight and they carry a very small footprint. We can deliver them to a customer location on the back of a flatbed truck or standard 20-foot shipping container. One of the areas that the EPS board is strongly committed to is to ensure that EPS turbines have a worldwide reach. Even in developing nations or in underdeveloped nations, we believe that everyone should have a right to clean, reliable power at affordable prices. EPS has had discussions with the government of Senegal and believe that it would be wonderful if EPS can participate in powering Africa to provide enough energy for villages to have clean drinking water through water purification facilities, enough power to run a school, power to run a hospital or a clinic, and to provide the internet to villages so they can stay in touch with the world around them. And I'd like to outline some of the benefits now of a potential investment in EPS. Three key things here, but green energy investments are increasingly seen as attractive in the private and institutional portfolios. In a few years' time, we believe that EPS will be ripe for a takeover bid or as an early IPO candidate. We have three strong reasons for you to consider an investment in EPS at this time. Firstly, we have very powerful economics due to our LOIs that have already been issued to us. We prepared a 7-year detailed financial projection. The forecast was based on input from our letters of intent from potential customers, and early market indications show very attractive sale growth, leading to attractive gross margins and high ROIs. Secondly, we strive for technological superiority with our turbines. We are thrilled with our partnership with Jim and his colleagues at Brayton. They have a very deep understanding of the turbine industry, especially the gas turbine industry. And quite simply, our biomass turbine is a game changer. Nobody else is doing it at this power range, and no other turbine engine in this power range compared with the efficiencies from our multi-fuel turbine. Thirdly, EPS is in a high growth market. Renewable energy through distributed generations is one of the fastest growing industry sectors. We have LOIs signed by 2 customers waiting to purchase significant quantities of our turbines. So, as I mentioned, we're seeking up to $18 million to complete this development stage. We've already raised $6 million. We need an additional $18 million. We want to have this money available to ramp up right to commercialization and become cash flow positive. We'll really accept and be pleased to accept any investment, individual investment over $500,000. We're going to be able to work with one or multiple investors. The funds here, we don't need it all up front. They can be injected in EPS over 10 quarters to coincide with predetermined milestones during the final development period. We will, when all is said and done, for the 18 millions, we'll be offering approximately 45% common share equity interest in EPS. And although we prefer a common share equity interest, we'll also consider other structures such as pref shares or senior debt. Of the 18 million needed in total, 12 million of that will be used to build the alpha unit that will be housed at Brayton's facilities in New Hampshire, and to build the two full-size beta units, one multi-fuel unit and a biomass beta unit, and both those units will be housed and continually tested at customer locations. Currently in the financial forecast, we have assumed in-house build-out of our assembly plant operations. In the first 12 to 15 months of this development stage, EPS will finalize our decision if we want to continue down the path of building internally or finalize our preferred route of outsourcing assembly functions to a third party who will assemble the EPS turbines at their facilities. And we've had discussions with a very well-known assembler. So that's another option we would strongly consider. And then part of the remaining capital from this raise will go towards the gearing up of assembly operations or hiring of sales and marketing force and general office expenses. We've looked at some of the where the 18 million will be used over the next 3 years or 2.5 years, outlined as a slide as a summary of the costs over this period and how they're expected to be incurred. As you can see, the alpha and beta unit build-outs comprise the lion's share of these costs. They're in lines 2 and 3. We have also forecasted costs for in-house assembly plant facility, including inventory, purchases, capital expenditures, and other assembly plant costs. At this time, that we don't anticipate any additional more capital funds to be raised beyond this 2.5 year development period due to the upfront payments, progress payments that we will receive from the sale of the commercial units that we can use and plow back into the company as working capital. Thus, it is anticipated that EPS will be a self-funding operation. I have included the list of major milestones that we expect to achieve over the 2.5 year development period. I will not go into detail of this, but you can see that we believe these milestones are achievable and realistic. If you could note that the full-scale alpha unit will be completed and 30% tested after 4 quarters of development, and the first commercial unit is expected to be built in Q2 2023 or in the 10th quarter of this development period. We have a full set of, as I mentioned, the 7-year detailed financial projection package. I've just outlined a few key components here. We believe that gross sales will ramp up quite quickly after the development period. It is planned that we will be running 2 shifts per day by the end of year 5 and already have or will be in the process of establishing a second assembly facility. Gross sales in year 7 are projected to be approximately 880 million. At the end of year 7, total assets are projected to be 495 million, with total shareholders' equity projected to be approximately 355 million. The ROIs will continue to increase until year 6, when we have projected to start paying dividends of about 20% of after-tax net income. The number of units assembled each day or each year is continually rising through the projection period. In year 6, we would project to be producing about 1.6 units per day. We anticipate we will have multiple worldwide locations performing these assembly functions at the end of the projection period. And just want to touch base again about the actual market that EPS is into. We've maybe touched on some of these points already, but just to reinforce these, the worldwide distributed energy sector was worth about $163 billion in 2016, and it's expected to grow to $573 billion by 2025. That's a huge increase, and it's really significant. EPS has the ability to transform the under 5 megawatt energy sector from its current focus on diesel-based engines to be now focused on very efficient EPS turbines. We're going to concentrate initially on the US, Canadian, and European markets, but we have already had discussions with Brazilian, Korean, and African officials about using EPS turbines. We have also discussed and would like to sell energy through PPAs and power purchase agreements. This element would be an upside to our financial projections, as currently not included in our forecast. A huge potential opportunity for EPS could be to own EPS turbine engines directly and provide and sell the power produced directly to a small or medium-sized town or village. In this case, EPS would sell power, not a turbine. And we would roll out this concept first in United States or Canada. This next slide shows the vast array of potential end users for EPS turbines. The opportunities are plentiful, as you can see from the chart, and are limited only to how one thinks about what markets could be converted to distributed energy applications. EPS sees high opportunities and potential opportunities in the commercial sector through the big box retail stores, shopping malls, and hotels. In the industrial sector, we see potential EPS targets being utility and power producers, as well as manufacturing facilities. And we also see growth opportunities in apartment complexes, housing developments, as well as universities and other educational facilities. And I'm going to turn the presentation now back to Jim.
Okay, so I'll just focus a couple of minutes on the competition again, and that's sort of largely two categories. There's a class of gas turbine engines that are competing our power level of 1 to 3. There's a few suppliers with notable names like Kawasaki and Solar and European group Kongsberg, which is part of Dresser-Rand, and Oprah, also smaller companies. And a U.S. company, Capstone, makes a very small engine, which they bundle together. They're all relatively small players in this market. The lion's share of the market goes to piston engine providers, and they're either a diesel engine or a natural gas engine or gasoline engine, or some big names there like Caterpillar and Jan-Bacher, which is General Electric, and Waukesha owns all of those two companies, Wärtsilä and Cummins and other big companies. So those are the principal competitors. The market segregation is that the piston engine companies are very competitive and they have very strong products, but they cannot burn most of the renewable energy fuels. They can burn expensive bio oils, but those are really too expensive to be competing in electric power generation. Same thing for the digester gas and some of those. We've gone around that problem so that we can use these low-cost bioderivative fuels directly in burning the shredded material or the solid material. So that saves a lot of chemical processing, and which drives up the cost of renewable fuels. And of course, we can burn other gases and such things as some of those engines, but with much better efficiency in lower emissions. So the next slide summarizes a few numbers in that. Next slide, please. So again, the first column, I'll just draw your attention to a few of the points. Again, comparing the efficiency of the two turbine companies, that'd be Solar and Oprah or Dresser-Rand. They have similar products. As I said, they're in the low 20 percentile efficiency, and their efficiency rolls off more sharply than the EPS engine, which is excellent part load efficiency by nature of its variable speed output. The other grouping, so the piston engines, for which there are many, as I mentioned, are sort of in two categories: the lean burn these are natural gas engines, so we excluded the diesel engines, but they're also, again, very efficient, but they have considerably more reliability challenges, limitations in the fuel they can burn, and they do require catalysts and such things. So they're not really in our competitive space so much because they cannot burn the fuels or and meet the emission standards that we want for this small power category. So looking down a list, emission levels, the NOx, the NOx, the CO, and the UHC, that's unburned hydrocarbons, are listed, and you can see the stark advantage that the EPS product offers over the other competitors. Gas turbines do fairly well on carbon monoxide, CO, but they have relatively high emissions, and they require very expensive after treatment to get into the California and into the European markets, while the EPS engine requires no after treatment and can already meet the CARB standards, the California Air Resource Board standards, without any after treatment. Other points, again, they're all substantial packaged systems. The EPS engine does have a substantial weight advantage, and that will ultimately translate into a cost advantage as well. It's a lot more compact and more economical product than the older gas turbine engines that were competing, or the piston engines. So I guess that's the principal thing. The no gearbox is required. It has an advanced high-speed generator in it, power electronics or inverter output system. Next slide, please. So I'll just speak for a moment about our team here. Again, we are a supporting player with the EPS engine and an investor in the program as well. We have roughly, again, a staff of about 50 people, and the majority of our team are engineers. We have, again, a core competency is in turbo machinery design, and we have special patent protection over the recuperator and some other things which we're licensing to EPS for their program. We are a research and development and a prototyping company, so we do a lot of in-house manufacturing and prototyping, but we're not the production supplier for this group here. But we have significant experience working with other customers and helping them get into production, and that's our intention with EPS, is that we're developing the early units and then helping them set up manufacturing production, and we've already laid out the facilities and factory for that, and work very intensively with third-party manufacturers to roll up the overall cost. I think that covers it. Next slide, please. That's yours, Mike.
Yep, thanks, Jim. We've received, as I mentioned, 2 letters of intent. One is from PowerSecure. PowerSecure is a Southern Company subsidiary, and Southern Company is a leading provider of innovative energy solutions to electric utilities and their industrial and commercial partners. PowerSecure provides energy solutions in the distributed power generation sector. The company is a pioneer in developing distributed power systems and the integration of distributed energy resources. They're focused mostly in Florida and Georgia right now, and their headquarters out of Wake Forest. I've met several times with the key senior officials of PowerSecure, including their CEO. They have signed a letter of intent to buy significant quantities of both the multi-fuel and the biomass versions of the EPS turbine. They're going to focus on the multi-fuel turbine to start, and they want to use approximately 70% of our units to purchase as peaker units that will be used for peak hour additional requirements to replace their aging recip engines. The second customer is out of Europe. It's called O2E, Organics to Energy. They're based out of the UK, but market focus is more in continental Europe. O2E produce synthetic fuels from plastic and organic waste materials. The CEO really likes our biomass unit and wants to buy units to be able to generate 300 to 500 megawatts of power capabilities through our biomass turbines, and O2E will allow EPS to install a beta prototype at their new R&D center. Just in getting towards wrap up here, the EPS board is currently comprised of 3 members, myself, Paul Benavides, and Catherine Kelly, who are all with me today. All of us are personally invested in EPS and have a long history with the company. Our bios are attached, so I don't need to go over them now on those 2 pages. And then right after that, we don't have any full-time employees hired to date. We didn't want to hire full-time staff before we had capital commitments secured. So we have been running a fairly lean shop. Personally, I have not been taking any money for compensation, and I've preferred doing it rather through common and preferred shares. EPS's progress to date has been made possible by the joint cooperation of 4 main parties, since we don't have a full-scale team yet of employees. Firstly, my fellow board members, Paul and Katie. Secondly, Jim and his team at Brayton. Third, there's former board members and other senior shareholders who have a background in engineering. And lastly, there's 3 special consultants to the EPS board right now, Doug Anderson, Steve Griller, and John O'Rourke, who I also lean on for market and technical guidance and assisting me with the capital raise exercise for EPS. And all of those people have, the special consultants have extensive backgrounds in turbine engines and the energy field. And the very last slide, I hope that Jim and I have imparted some knowledge today on the distributed energy sector and how EPS is ready and able to become a big part of it through its advanced turbine engine technology. I hope you will consider learning more about EPS and how we could become this could be a very exciting investment opportunity for your family office. I can be reached at phone or by phone or email address at the numbers above, and please don't hesitate to contact myself or Jim if you have any questions. Thanks for your time today, and I'll turn the session over to Lindsay, who will monitor the Q&A session. Lindsay?
Thank you, Mike and Jim. Yes, Mike mentioned, we would love to encourage questions. So please, again, use your questions chat option on your screen if there is anything that you would like to get answered. And Mike, as we wait for questions to come in, if there are any, is there anything else you would like to add, or Jim?
No, just to say that EPS believes we're in the right place at the right time. We have a great team with Brayton, and we believe the future looks very bright for EPS and the distributed energy sector right off the bat. We think that we're very flexible in what we can do, and there will be a breakout of these smaller scale 1 to 5 megawatt turbines that will compete very favorably against its other competition and against solar and wind providers as well. Jim, do you have anything you want to add?
Well, I'm available for any technical questions. I guess that's my department. So
Yeah.
We're working very hard to meet these demanding goals of the technical development team.
Well, on behalf of everyone at Family Office Networks, we thank all of you for joining and attending today's webinar with EPS Holdings. As I already mentioned, we'll be following up with all of you individually. Mike and Jim, thank you so much for your time today. We hope everyone has a great day.
Thanks a lot, Lindsay.
Thanks, Mike.
Thank you.
Bye.
Have a great day. Thank you.